Same disclaimer, make sure you take the test, then look at the answers. Score yourself honestly, email me your score. Question 29, you've seen this before, I think I put this on test 3 actually, but we'll go through it again because it never hurts to see it again for practice. So what we have here is a block that's being pushed by a 20 Newton force, and then it's pushed into another block, right? So the 20 Newton force doesn't directly act on the 2 kilogram block, but the 3 kilogram block exerts a force on the 2. So I want to remind you of the general narrowing our focus to make the force that we want external to the system. Well, the force that we want is the force that the 2 kilogram block exerts on the 3 kilogram block, right? So how do I make that external? I focus on only the 3 kilogram block. So the sum of forces, and this subscript here denotes the system. In other words, this is on the 3 kilogram block only. I'm not looking at the 2 anymore. So it's the 20 Newton force pushing it to the right minus the force of the 2 kilogram block, which pushes leftwards on the 3, is equal to the mass of only the 3 kilogram block now. See? I don't use 5 again because my system has changed. Times the acceleration. But wait, Mr. Gussman, that doesn't make any sense. Why would you change your mass here but not change your acceleration? Again, that's what I was saying about why we solve for acceleration first. It's the same for each block as it is for the whole 2-block system. So it's the only thing that's kind of the same for all of them. That's why you want it. It's the most useful quantity to have. Now we can solve this. So it's 20 minus x equals 12, basically. And you end up with 8 newtons. And the reason that the answer choice is to the left is, like we said a moment ago, the 2 kilogram block is on the right side of the 3. And so it will push or exert a normal force this way. Now that force is less than the 20 newtons over here. That's why the acceleration is still to the right. But it does exert a leftwards force, which diminishes the acceleration that the 3 kilogram block would otherwise experience if the 2 were absent. To analyze oscillation, which you don't know how to do yet, so don't worry about it. Let's see if you guessed it right, but here's how you actually do solve this type of question. This formula is on your equation sheet. It is the period of a mass oscillating on a spring. 2 pi is a constant, m is the mass of the block, and k is the spring constant. Therefore, 2 and pi being constants, we can say that the period is proportional to the mass of the block over the spring constant. And if you go back to the prompt, it told us that the spring was stretched a distance d by the mass m. So before the system is set into oscillatory motion, if it's at rest, then the forces would be balanced. So let's do a sum of forces on the block as it hangs from this vertical spring, but it's motionless. The force of the spring minus the force of gravity would be equal to 0. And if we remember Hooke's law, the force exerted by any spring is negative kx. But it's important now to remember what that negative sign is for. It just tells us that the direction of the force exerted by a spring is always against the direction of the spring's displacement. So if I pull the spring right, it pulls back to the left. If I push the spring left, it pushes back to the right. Therefore, we have to just choose the direction that should go in here in my sum of forces based on the actual direction the spring force acts on the block. And since, let's try to draw it a little bit here. So we've got this vertical spring, and it is suspended like so. Well, gravity is down, and the spring force, in this case, is up. And therefore, even though Hill's law says to use a negative sign, I'm going to use a positive sign for my spring force, only because I've chosen up as the positive direction. So my force diagram would look like this. I have a force due to the spring of magnitude kx, which is then balanced with the downwards gravitational force of magnitude mg. There we go. Therefore, kx equals mg. And I'm going to change x to d. Remember, x is the displacement of a spring from its equilibrium position. That's like a general definition of x. But d is the problem-specific displacement of the spring. It gives us this distance that the spring was stretched. Solve this. We get an expression for the spring constant k. So what I'm going to do now is I'm going to take this expression for k, and I'm going to plug it in for k. So I do that. Mg over d is in the denominator. Let's do a little fractional math. You get m over m here, and that becomes 1 over g over d, and that's the same thing as d over g. And therefore, your answer is the period is proportional to the distance over the acceleration due to gravity. Energy function with respect to position, and we want to figure out the force. To do this, we need to know a relationship between force and potential energy. Alright, so here's an equation we introduced in Unit 8 when we talked about energy. The work done by any conservative force is equal to the negative of the change in the potential energy, and therefore I can replace the work conservative, the left side of the equation, with this expression, f of x dx integral, and that's the expression for work. That's just like the general formula for work done by any force, actually. It doesn't matter if it's conservative or not. So if I do a little algebra, we can rearrange this and solve it for the force, and it is the negative position derivative of potential energy, or it's negative du dx. Therefore, if I start from a function of potential energy with respect to position, all I have to do is take the derivative and then evaluate it at the moment we care about. So starting with the derivative, this is just power rule once again. You notice a trend. And I guess I just wrote the same thing twice there, whatever. Okay, anyway, so here's the actual derivative. It's negative 12x minus 4. And if I evaluate that at position x equals 3 meters, we get negative of 36 minus 4, which is negative. And that's why the answer choice is B rather than A. It's because of the negative sign in my answer. Or one rock, I guess. One rock is dropped and the other is thrown. They both have the same initial y velocity. VOY, which is how fast they are moving up or down at the instant that the motion begins, is 0. Right? If you drop something, its velocity is 0 in every dimension. But if you throw something horizontally, it is moving, let's say to the right, only in the x dimension. It doesn't have a component in the y dimension. So VOY is 0 for both, and therefore, in the absence of air resistance, and it says air resistance is negligible here, they will reach the ground in the same amount of time. So now we can solve. So the first thing to do is think about what formula we're going to use to solve once we have all the information. And it's this one. We know the displacement. We are looking for the initial velocity in the x dimension. And we need to know the time then to finish. Like I said, though, these two things hit the ground in the same amount of time because they have the same initial y velocity. So we'll just use kinematics in the y dimension. Both of them start with a y velocity of 0. So this is actually the equation for either or both rock, the thrown and the dropped rock. They start at a position of 45 meters. They end at a position of 0 meters. And we can use the acceleration due to gravity because this is a projectile. And again, that's only valid because we're analyzing the y dimension only. You can only do that if you're looking at the y dimension only. So solve this and you get a 3-second time period. Now that we know the time, that goes back in for time up here in the top equation. And because I already know the displacement from the prompt, which is 30 meters, I just solve this and you get 10 meters. Once again, the formula for a mass on a spring is, or the period of a mass on a spring, is in your equation sheet, and it is 2 pi times the square root of the mass of the object over the spring constant. So we'll just take out the constants here. We know 2 and pi are constant, and we also know that the mass of this object is constant, like it's the same for both of them. So K is in the denominator, so how does K impact the period T? Greater spring constant, shorter period, inverse proportion. Made it. Satellite moves in a stable orbit, blah, blah, blah. So before I even read the rest of this, I said this a few slides ago, but I'm going to say it again. As soon as you see satellite or orbit or any of these sort of keywords, astronaut maybe, you immediately should think of universal gravitation. That's gonna be your strategy for, like, I don't know, 75% of these or so. And it will be here as well. So what we want to figure out how fast must this satellite be moving in order to have an orbit of distance 2r if its orbital distance r produced a speed v sub 0. So like I said, here's the formula we're going to use for almost all of these questions. One twist though. So here's universal gravitation. This is the force of gravity, right? What's this side? What's this other stuff over here? You might recognize this. This is the formula for the sum of centripetal forces. So what I'm saying is that the force of gravity, which is the only force that acts on a satellite, is the sum of centripetal forces. Sum of centripetal forces, or we sometimes say radial forces. Those are synonymous. And the sum of centripetal or radial forces, let me put a subscript over here, is equal to mv squared over r. So that's all I've done. So let's kind of think about which m is which now. I think I've made it clear because one is capital, one is lowercase, but that won't always be the case on, if it's not me giving the problem to you. So what m is this? What is the m in mv squared over r? Well, again, that comes from a circular motion equation, so it would be the mass of the object that is moving in a circle. And that would mean the mass of the satellite. So we would cancel out the mass of the satellite on both sides. And there's also an r in the denominator on both sides. So we lose one of the r's, and there's the one on the left side remaining. Solve this for velocity. You end up with the square root of gm over r. Therefore, your velocity is proportional to the square root of 1 over the distance, or the radial distance, the orbital distance. And that means your final velocity, if you were to double r, put in a 2r instead of r here, How would that be different from the original expression? Well, it would just be the square root of 2 in the denominator. So it's the initial velocity over the square root of 2.